Hello, welcome to Module 5 of the course on application of spectroscopic techniques in molecular structure determination. In this module, we see some special cases of structure elucidation. A problem solving session is what we are going to have in this particular module. We look at some stereochemical aspects of compounds which can be identified by proton NMR spectroscopy. Now let us go to the first slide. Now the question here is effect of molecular symmetry. What does it do to the NMR spectrum? We have already seen in the earlier example, if the molecule is highly symmetrical in nature, then you get a fewer number of signals in the NMR. Now the question that is posed here is, let us say ketene is undergoing dimerization. What is the structure of the dimer? Will it have a structure which is this particular structure, which is a lactone structure, or will it have a structure which is this particular structure, which is a diketone structure? Essentially, the difference between these two structures is that this is a highly symmetrical structure, whereas this is an unsymmetrical structure. The actual spectrum of ketene seem to be showing an unsymmetrical pattern. In other words, it has three different chemical shift values corresponding to these two hydrogens corresponding to one chemical shift value, and this hydrogen which is trans to the oxygen here, and this hydrogen which is cis to the oxygen here comes at two different chemical shift value which are shown here. So essentially the ketene dimer spectrum is this particular spectrum. This would match only with this particular structure. It would not match with this structure. In fact, the structure of the other compound is shown here and the spectrum is also shown here. Because of the highly symmetrical nature of this molecule, there is only one singlet that is seen for all the four hydrogens, around 3.55 ppm or so. So the fact that you have three different chemical shift values indicates this is the unsymmetrical structure is what is most suited for the dimer of the ketene, the structure of the ketene dimer to be this particular structure and not this particular structure here. Another example we will see here. This is again a symmetrical molecule. It's a very fairly simple molecule. This CH2, which is flanked by two oxygen, comes at the most de-shielded region in the NMR, around 4.5 ppm it comes as a singlet because there are no coupling partners, there are only oxygen adjacent to this. Then you have an ethyl group on this side, another ethyl group on this side. Because of the molecular symmetry, these two ethyl groups are identical in nature in terms of their chemical environment. So a single set of quartet and a triplet is what you see for both the ethyl groups. So the integration ratio would be corresponding to 2 hydrogen here, 4 hydrogen here and 6 hydrogen here in terms of the relative intensities of the ratio. Now let us ask ourselves this question. Suppose I introduce a substituent here at this position in the form of a methyl group. What happens to the NMR spectrum? This simple spectrum turns into a fairly complex spectrum upon introducing a simple methyl group at this position, because now the molecule loses its symmetry. We are now talking about this particular molecule. You can see here this spectrum is a much more complicated spectrum compared to the earlier example of this particular compound spectrum, which is a simple quartet and a triplet and a singlet. This particular introduction of a methyl group at this methylene position here has caused enormous changes in the NMR spectrum of this compound. Now what is the reason for this? Let us analyze this. There is a quartet here and a triplet here. This quartet is essentially a 1 hydrogen intensity and this triplet here is essentially 6 hydrogen intensity. So they are not essentially because of an ethyl group which normally we encounter in this particular case. So the ethyl group is actually, because it is connected to oxygen, this methylene should come in the region, typically in this particular region. There is one hydrogen which is the methine hydrogen, and that is split by the CH3 into a quartet, and that lone hydrogen alone comes in this particular region of 4.8 ppm, because that will have the highest chemical shift value because it is flanked by two oxygen. So the 4.8 ppm quartet corresponds to this particular hydrogen, the position that I am pointing with this cursor here. That particular position hydrogen is what is responsible for it. It is a quartet because it is split by this methyl group, which is 3 adjacent hydrogens are there. Therefore it is a quartet. Now what happened to the methyl itself? The methyl is split into a doublet. So you can see a doublet here, for example, and this methyl is essentially split by this methine hydrogen into a doublet, and you can see the methyl group with the 3 hydrogen intensity being a doublet in this region of about 1.3 ppm or so. Now this methylene, which should have been a quartet, is not a quartet anymore. It appears to be a fairly complex multiplet. It is because this is a prochiral center and that makes these two hydrogens pro-diastereotopic in nature. In fact, the two hydrogens are diastereotopic in nature, so they will split each other into a doublet of a doublet 4-line pattern, which is further split into by the CH3 into a quartet. So a doublet of a quartet is what one should see for the spectrum. This region of quartet and this multiplet is expanded, and it is shown in this particular slide. This methane hydrogen appears as a quartet, and this methylene appears as a doublet of a quartet. In other words, this is an overlapping quartet for one of the hydrogen, and this is an overlapping quartet for another hydrogen. If you count carefully, you can actually see 16-line pattern in this multiplets for the corresponding to the methylene group of this. The CH3 appears as a simple triplet, which is shown here. So both the CH3s are identical. These ether CH3s are identical, for example, and both of them appear as a single triplet of 6 hydrogen intensity for this methyl and this methyl put together. So this example essentially illustrates that a small perturbation by introducing a methyl group causes a fairly large change in the NMR spectrum in comparison to a more symmetrical structure like this. The less symmetrical structure becomes a complex spectrum, and wealth of information is obtained because of the complexity of the spectrum. Now, quite often we ask the student whether it is possible to distinguish this cis and trans isomers using NMR spectroscopy. The immediate conclusion or the answer the student gives is that yes, it is possible to determine by the NMR spectroscopy by the coupling constant between these two hydrogen is the standard answer that one gets. This is a wrong answer, of course, because these two hydrogens in this molecule or these two hydrogen in the cis compound, they are chemically equivalent and they don't split each other at all. They are magnetically as well as chemically equivalent. So what one would see in the spectrum is a singlet for these two hydrogen. There won't be any coupling to show whether it is a cis coupling or trans coupling. Similarly, these two hydrogens also, they are chemically and magnetically equivalent. So they would also appear only as a singlet. We will see the spectrum in the next slide. This is a spectrum of cis tilbene. You can see here this singlet, which is shown by this arrow here, corresponds to these two hydrogen. The phenyl appears as a multiplet of 10 hydrogen intensity in this position here, and these two hydrogens are essentially coming as a singlet. So there is no question of J value to be distinguishing this cis isomer from the trans isomer. Let us see the spectrum of trans isomer. The trans isomer also is a singlet. For these two hydrogen, olefinic hydrogen appear as a singlet of 2 hydrogen intensity, and the phenyl groups appear as the multiplet, fairly complex multiplet of 10 hydrogen intensity. So the point is that symmetrical structures do not offer you information regarding coupling because of the chemical equivalence and magnetic equivalence of this type of hydrogen. So how does one now determine which is the cis and which is the trans? Now, if we have the spectrum of both the cis as well as the trans isomer, it is possible to rationalize which is a cis one and which is a trans one. In the cis one, the two hydrogens are away from the anisotropic effect of the phenyl group. So therefore, the chemical shift value of these two hydrogens in comparison to the trans isomer should be lower. In fact, it comes around 6.5 ppm or so. The trans isomer, if you see, it is coming slightly above 7 ppm. This hydrogen is flanked by these two phenyl groups, so is this hydrogen by these two phenyl group. So the anisotropic effect of these phenyl groups will be strongly felt by the proton, causing it to de-shield itself, and as a result of that, compared to the cis isomer which came around 6.5 ppm, the trans isomer in fact comes, the two hydrogens come above 7 ppm. Thereby is possible to identify on the basis of chemical shift, not on the basis of coupling constant, because there is no coupling constant associated with this molecule. Now, what about this cis dichloro derivative and trans dichloro derivative? At least in the case of phenyl derivatives, we talked about anisotropic effect and ring current effect and the de-shielding effect and so on. And such a facility does not exist in the case of trans dichloro derivative. Can one distinguish or can one get the J value between these two hydrogens which are apparently not coupled to each other? Is it possible to obtain the J value of the two protons indicated in these isomers? That is, there is no coupling, apparent coupling between these two hydrogens. Then how does one get the J value is the question that we are addressing. In order to do that, we look into a phenomenon called carbon-13 satellite peaks. We are actually referring to only a proton NMR spectrum of the compound. When you take this trans isomer, the trans dichloro derivative, the actual sample contains mostly 99% of the molecules are carbon 12 and carbon 12 molecule, and carbon 12 of course is magnetically inactive, so it doesn't matter for the NMR experiment. So these two hydrogens are chemically and magnetically identical in the carbon 12 carbon 10 isotopomer of the trans dichloro-derivative. However, remember the natural abundance of carbon 13 is about 1%. So the probability of having a carbon 13 labeled, naturally abundant labeled carbon 13 compound is about 1%. In other words, if you have 100 molecules, 99 molecules with the solution would be of this type and one molecule will be of this type. So it should be possible to record the spectrum of this mixture and pick out the spectrum of this particular sample. Why is it important to pick out the spectrum of this particular sample? Because this is carbon 13, it is magnetically active, and that makes these two hydrogens non-equivalent in terms of the magnetic equivalence. They are chemically equivalent but magnetically non-equivalent in their nature. So one should be able to see the splitting between these two hydrogens in the carbon 13 isotopomer of the trans dichloro-derivative. Now you can ask the question, how come you don't have a molecule where both the carbons are carbon 13? That would be much less abundant. It will be 1% of the 1% of the molecule that you have here. In other words, 0.01% of the molecule would be having carbon 13 and carbon 13. So it would not be possible to detect such an sample because of the low abundance of carbon 13 in the natural abundance. Now what would be the spectrum of this molecule? These two hydrogens are chemically and magnetically equivalent, so it just gives only one line pattern. Here these two hydrogens are magnetically non-equivalent, chemically also they are equivalent. Chemically they are equivalent but magnetically non-equivalent in nature, so it should be actually A and A prime in terms of the label that one should give, not A and M. There is a mistake here. Now in the absence of carbon 13, only carbon 12, it would have given a singlet. Because of carbon 13 being present here, this particular hydrogen that is directly attached to the carbon 13 will have a large coupling of the order of 100 plus hertz or so. So that is split into a doublet, which is seen here. This will be further split into a doublet by this H, which is this particular H, because this is magnetically non-equivalent in nature. So the carbon 13 essentially splits the hydrogen in the proton NMR spectrum into a doublet, and the doublet is further split into a doublet by this HM, which is this doublet that you are seeing here. So this large coupling is the carbon 13 hydrogen coupling, one bond coupling, and this small coupling here that you see here is the hydrogen coupling. That is the question we asked, can we get the coupling constant between these two apparently non-coupled hydrogens in a molecule like this? Yes, it is possible if you look at the carbon 13 satellite spectrum. Please remember, carbon 13 satellite spectrum is actually a proton spectrum of the carbon 13 isotopomer of the sample that we have. So what happens to this hydrogen now? This is away from one carbon, away from the carbon 13. So that coupling, which will be much less, of the order of tens of hertz. So that is split into a doublet here, and it is further split by this hydrogen into a doublet. So again you will see a doublet of a doublet. What you will see is essentially a symmetrical pattern on either side with respect to the singlet which should have appeared in the system. The actual experimental spectrum is shown in the next slide. This is the spectrum of carbon 13 satellite spectrum of the 1,2-dichloroethylene. So this huge peak that you see in the middle is actually because of the 99% of the carbon 12 isotope of dichloroethylene. There is no splitting, so it just appears as a singlet. These two tiny lines that you see here, which is expanded, zoomed into the bigger picture that's seen here, indicated by the arrow. There are two lines here and two lines here which are expanded and shown as an expansion here. And this is essentially because of the carbon 13 splitting of this line into a doublet, which is further split by the hydrogen, which is this particular hydrogens are splitting each other, for example. So the J value between the two hydrogens are essentially gap either here or the gap between these two lines here. So it is possible to get the J value of apparently non-coupled system if you look carefully into the carbon 13 isotopomer spectrum of the corresponding molecule. Now let us solve a problem, a chemical structural problem here. We will try to identify the chemical shift value, J value. The purpose of this exercise is essentially to familiarize with the logical way of deducing the structure of an organic compound from the molecular formula and the spectral pattern that is given here. From the molecular formula, one comes to the conclusion that double bond equivalence of this compound is about 3. Now there is a singlet at 3.8 ppm of 3 hydrogen intensity, so one can assume because of the presence of oxygen this to be a methoxy functional group. Now the multiplet at 6.4 and 4.6, we will see what kind of multiplet it is in the next slide. For the time being, assume that this is one multiplet and this is another multiplet. This comes in the olefinic region, so you have a olefinic proton, two olefinic protons, so you have a C2H2 fragment in this particular moiety, and you have a OCH3 fragment in this moiety. If you subtract this C2H2 and the OCH3 from the molecular formula, what is left with is C2H. Now you have to have double bond equivalence of 3. You have accounted for one olefinic bond here corresponding to a double bond equivalence of 1. So you have to now account for 2 more double bond equivalence. That is where this multiplet comes into picture. What is this multiplet at 3.1? Can it be due to an acetylene? Because acetylenes typically come in the region between 2 to 3. So typically an acetylenic hydrogen can actually come in this particular region. So if you assume this to be an acetylenic hydrogen, the C2H fragment which is remaining after subtracting these two fragments from the molecular formula would satisfy the double bond equivalence of this particular system. So it is possible that this molecule has a triple bonded structure, a double bonded structure connected to a methoxy functional group. So this is these multiplets, the multiplets that you see here are expanded, and the expansion is what is shown here. There is a multiplet at 6.4 ppm, there is another multiplet at 4.6 ppm, there is another multiplet at 3.1 ppm. All these three multiplets are essentially doublets of doublets, as you can see here. 6.4 ppm doublet of a doublet, 4.6 ppm doublet of a doublet, 3.1 ppm doublet of a doublet. In other words, these three hydrogens are mutually coupled to each other. That's what it means. For the sake of clarity, the frequencies of these lines are also given here. Line 1, 2, 3, 4 corresponds to the 4 lines of the 6.4 ppm chemical shift multiplet, and lines 5 to 8 serial number corresponds to these 4 lines. Lines 9 to 10 corresponds to these 4 lines also. So if you want to calculate the coupling constant value from these multiplets, what I have done is calculated the coupling constant value. You subtract line 2 from line 1, you get 0.5 Hertz, 0.48 or something you get for the coupling constant. Similarly, you subtract 3 from 4, then also you get the same value. So one of the coupling constant is roughly 0.5 ppm or so. Now you take the mid portion of the between 1 and 2, you take the middle center point of 1 and 2, which would be something like 1922.5 or so. This would be 1916.5 or so. That is the average of 3 and 4 and the average of 1 and 2, and take the average of the average. That would correspond to something like 6 Hertz in the spectrum. Likewise, you can calculate the gap between these two lines here. That would correspond to something like 6 Hertz. And you can calculate the gap between these two lines here. That would correspond to something like, this would correspond to 3 Hertz, and this would correspond to something like 6 Hertz or so. And finally, if you calculate the midpoint of this to the midpoint of this, that is about 6 Hertz. So you have 3 different types of coupling constant. One set is coming from the doublet of a doublet here as 0.5 and 6. Another set is coming from the doublet of a doublet at 4.6, coming as 3 and 6 Hertz of coupling constant. The third one is coming around 3.1 delta value multiplet as a coupling constant 0.5 and 3 Hertz values. The structure of the compound is satisfied, the data is satisfied by the structure of this particular compound, namely the cis isomer of the methoxy butene. This is methoxy butene because you have a methoxy peak in the NMR spectrum which corresponds to the singlet around 3.8, and then you have a olefinic hydrogen. There are 2 olefinic hydrogen and 1 acetylene hydrogen. If you put all these fragments together, this is a kind of structure that one can come up with. Now what are the coupling constants we have measured? We have put specifically the cis isomer because there are no couplings greater than 10 Hertz in the coupling partners that you have here. The coupling constants are 6, 3 and 0.5 only. Nothing is more than 10 Hertz coupling. So it cannot be the trans isomer. So H1, H2 corresponds to the vicinal coupling of about 6 Hertz. And H1, H3, which is the 1, 2, 3, 4, 5 bond coupling, is a very small coupling of about 0.5, and 2 and 3, which is about 1, 2, 3, 4 bond coupling, is about 3 Hertz or so in this particular case. Now, the chemical shift values of these two olefinic hydrogens, if you look at, the lone pair of electron of the methoxy can be delocalized onto this carbon. This is like an enol ether. In the case of enol ethers, the beta carbon is always electron rich, and as a result of that, that particular hydrogen is going to be coming at a shielded region, much lower delta value compared to the alpha hydrogen of the enol ether. So, we put the H1 at the highest delta value of 6.4 because it is attached directly to the oxygen bearing carbon, and the beta position is electron rich in nature because of the delocalization. So, that is highly shielded, 4.6 ppm or so. Finally, the acetylenic hydrogen, which is the most shielded, comes around 3.1. The trans isomer is incorrect answer because the J value is not, J values are less than 10 Hertz. The structure satisfies in terms of delta value as well as the J value as well as the double bond equivalence of this compound. So, this gives you an illustration of how to extract the information of chemical shift values and coupling constant values and logically solve the structure of this simple molecule of this kind. Thank you very much.